There is a warmth settling on your skin right now, so gentle you may have stopped noticing it, arriving after a journey so vast that the number of minutes involved barely means anything to a body sitting quietly in a room. Even with your eyes closed, even in the dark of a bedroom with curtains drawn, the air around you carries a little of this warmth, borrowed and passed along, wall to wall, until it settles against you like a hand that means no harm. It has traveled through empty space for about 8 minutes to reach the top of the atmosphere, and then a little longer still, bouncing and slowing through air, before it becomes simply the mild temperature of the room you are lying in. Close your eyes, and you can still feel it, faintly, the way you can feel a fire across a room. Somewhere above the horizon, or perhaps below it now, hangs the source of that warmth, and tonight we are going to travel toward it, slowly, the way you might approach a place you have looked at your whole life but never actually visited. You have seen the sun so many times that it has become almost invisible through familiarity, a bright disk, too dazzling to look at directly, sliding across the sky in an arc that changes gently with the seasons. Children draw it as a yellow circle, with lines coming off the edges, and in a way that childhood drawing is not far from how people pictured it for most of human history, a flat, glowing thing stuck to the inside of a dome, or a chariot pulled by unseen horses, or a god's eye watching the day unfold. The ancient Egyptians called it Ra, and imagined it sailing a boat across the sky each day and through the underworld each night. The Greeks had Helios driving a blazing chariot from one horizon to the other. These were not foolish ideas. They were careful attempts, using the tools available at the time, to explain something enormous and mysterious, using the only language available, the language of everyday human experience, of boats and chariots and journeys. It took a very long time, and a great many careful, patient observers, to begin peeling back the layers of that mystery. The Greek philosopher Anaxagoras, more than 2,000 years ago, was one of the first people we know of to propose something startling, that the sun was not a god or a chariot at all, but an enormous glowing stone, larger perhaps than the entire region of Greece. For this idea he was accused of impiety, and eventually driven from Athens, a reminder that looking closely at something people had always accepted as mysterious can sometimes be seen as a kind of trespass. Centuries later, astronomers with early telescopes began to notice dark spots drifting across the sun's face, and arguments broke out about what those spots even were. Blemishes on a perfect, unchanging heavenly body seemed almost unthinkable to some, and yet there they were, appearing and fading over the course of weeks. Tonight we are not going to stop at the surface, at the bright disk itself, the part your eyes would perceive if you were unwise enough to look at it directly. We are going to go further, and slower, and deeper than any spacecraft has ever managed to travel. This is worth pausing on for a moment, because it is a strange and almost humbling fact. Human beings have sent machines to land on the moon, to roll across the dusty plains of Mars, to fly past the icy rings of Saturn and the strange blue haze of Neptune. A spacecraft has even touched the surface of a comet, a small dark wanderer of ice and dust, drifting far out in the cold. And yet no machine, no probe, however cleverly built, however heavily shielded, has ever come close to touching the sun itself, let alone entering it. Even the most advanced solar probes, engineered with heat shields of a kind that did not exist a generation ago, are designed only to graze the very outer edges of its atmosphere, dipping in and quickly pulling away again,
like a swimmer testing water that is far too hot for anything but the briefest touch.
So how, you might reasonably ask, does anyone know what lies inside it? How can we speak with any confidence about a place that light itself takes many thousands of years to cross, when even a spacecraft cannot approach its outer skin? The answer, and it is a strangely beautiful one, is that we do not need to go inside to begin understanding what is there. In much the same way, a physician can learn about the working of a heart by listening to it through a stethoscope without opening the chest at all. Scientists have learned to listen to the sun. Its surface trembles and ripples in slow, rolling patterns, oscillations that reveal something about the layers and currents churning far beneath, the way ripples on a pond can hint at a stone dropped somewhere unseen below the surface. There is also its light itself, split apart into a rainbow of color and studied line by line, each thin, dark gap in that rainbow acting almost like a fingerprint, telling us what kinds of atoms are present in the outer layers. And there are the tiny, nearly weightless particles called neutrinos, born deep within its core and passing through the entire body of the sun, then through the vacuum of space, then through the solid earth beneath your house, almost as if none of it were there at all, arriving in underground laboratories built specifically to catch the rare few that interact with anything on their way through. Piece by piece, clue by clue, indirect evidence gathered patiently over more than a century, scientists have assembled a picture of the interior of the sun that is remarkably detailed, even though no eye and no camera has ever looked upon it directly. This is one of the quieter triumphs of human curiosity, that a place forever closed to direct observation can still, in a sense, be visited, mapped, and understood through nothing more than light, vibration, and the occasional wandering particle. So let us begin the journey properly, the way any long trip begins, at the point that is easiest to see. Picture the sun as it appears from Earth at a comfortable distance, a smooth, bright, seemingly unmarked circle hanging in a blue or darkening sky. From here, it looks almost gentle, almost still, the kind of steady presence that rises and sets with such reliability that entire calendars, entire ways of measuring the passage of days and years and seasons were built around its movement long before anyone understood what it actually was. It looks, from this distance, roughly the size of a coin held at arm's length, a small and unremarkable disk that somehow manages to light an entire sky and warm an entire planet. Now imagine drawing closer. Not suddenly, not the way a spacecraft accelerates toward a target, but slowly, the way a diver might descend through the layers of the ocean, pausing to notice how the light changes, how the pressure shifts, how the water itself seems to become a different substance the deeper one goes. As the disk grows larger and larger in your imagined view, its edges begin to change. What looked like a smooth boundary from far away becomes softer, hazier, less like the edge of a solid ball and more like the edge of a flame or a cloud, something without a hard surface at all. This is one of the first surprises waiting at the threshold of this journey, something worth sitting with for a moment before we go any further inward. Because unlike the Earth, unlike the Moon, unlike almost every solid object you have ever touched or stood upon, the sun has no surface in the way we usually mean that word. There is no ground to land on, no crust to walk across, no boundary where gas ends and solid begins. What looks, from 93 million miles away, like a smooth and finite disk, is in fact something closer to a very gradual thinning,
a place where the material of the sun simply becomes transparent enough for light to finally escape into space, rather than a place where one substance stops and another begins. It is less like the skin of an apple and more like the point in a fog bank where you can suddenly begin to see the road ahead, the fog having no true edge, only a gradual dispersal into clearer air. That soft, glowing boundary, the closest thing the sun has to a face, is where we will pause next, resting there a while before we let ourselves sink further down, past the light, into the slower and stranger layers that lie beneath it.
Let's stay with that idea a moment longer, this notion of a star with no true edge, because before we sink through that glowing boundary and into the slower layers beneath, it helps to understand just how much material we're actually talking about, how large a thing we're preparing to enter. If you could somehow scoop out the Earth and set it beside the sun, hollow the sun out, and start filling it back up with Earth-sized planets, you would need something like 1,300,000 of them to fill the space completely. That number is difficult to hold in the mind in any real way, so let it sit loosely, the way you'd let a very large number of grains of sand sit loosely, without trying to count them one by one. Picture instead something simpler. If the sun were the size of a large beach ball, roughly 2 feet across, the Earth on that same scale would be smaller than a peppercorn, orbiting that beach ball at a distance of about 215 feet away, roughly the length of 2 tennis courts laid end to end. Everything you know, every mountain, every ocean, every person who has ever lived, would fit on that single, tiny peppercorn circling a beach ball of fire. And yet, for all that size, the sun is not some impossibly dense or exotic thing. Its average density, taken as a whole, is only about 1 4/10 times that of water, which means that if you could find a lake large enough and somehow keep the sun from doing what a star naturally does, it would very nearly float. This tells us something important right away, something worth carrying forward as we go deeper. Despite its staggering size, the sun is not solid. It is not even, in most places, especially dense. It is a ball of gas, mostly gas, held together and shaped entirely by its own gravity, gas pulling in on itself from every direction at once, with nothing but more gas to push back. That composition is worth naming plainly, because it will matter for everything we explore later. The sun is made overwhelmingly of hydrogen, the simplest and lightest element there is, just a single proton with a single electron circling it, accounting for something close to 3/4 of the sun's mass. Almost all the remainder is helium, the second lightest element, quietly built up over billions of years by the very process that makes the sun shine, a process we'll come to in its own time. Everything else, the oxygen, the carbon, the iron, the tiny traces of nearly every other element found on the periodic table, adds up to less than 2% of the total. In a sense, if you wanted to describe the sun honestly and simply, you might say it is a sphere of hydrogen slowly turning into helium, glowing as it does so, and that description would not be far from the truth. The age of this process is worth pausing on too, if only because it helps explain why the sun behaves the way it does, why it burns steadily rather than erratically. Scientists studying the oldest rocks in the solar system, meteorites that have drifted largely unchanged since the very beginning, have arrived at an age for the sun of about 4.5 billion years. Give or take a small margin of uncertainty,
that continues to narrow as measurements improve.
4.5 billion years is long enough that the sun has been shining, essentially in its current form, for roughly a third of the entire age of the universe. It has been doing this quietly, without fanfare, for far longer than there have been eyes anywhere to watch it. Here is where gravity enters the story in a more active way, because a ball of gas this size, left with nothing to oppose it, would not simply sit still. Gravity is always pulling every particle of the sun toward its center, every proton, every electron, every stray atom of iron or oxygen, all being drawn inward by the combined mass of everything else. Left unchecked, this pull would cause the whole structure to collapse in on itself, the way a sandcastle collapses when the tide finally reaches it, or the way a pile of loose snow settles and compresses under its own weight. And in a sense, this is exactly what almost happened long ago when the cloud of gas and dust that would become the sun first began to draw together under its own gravity, growing denser and denser as it fell inward on itself. But collapse is not what we see when we look at the sun today, and the reason is pressure, the same basic kind of pressure you feel when you push down on an inflated balloon and feel it push back. As that original cloud of gas contracted, the material at its center grew hotter and hotter, the way air in a bicycle pump grows warm as you compress it quickly, and eventually the core reached temperatures and pressures great enough to ignite the process of nuclear fusion, hydrogen fusing into helium and releasing tremendous energy in the process. That energy moves outward, pushing back against the inward pull of gravity, and somewhere in that push and pull, the sun found a kind of balance, a state that scientists call hydrostatic equilibrium. It is a delicate phrase for a very simple idea. At every point inside the sun, the outward push of hot gas and radiation pressing against its neighbors above is exactly matched by the inward pull of everything above pressing down. Not shell against shell, not layer locked against layer, but a continuous, breathing balance that exists at every depth simultaneously, adjusting itself instant by instant. It may help to think of this less like a building held up by walls and floors, and more like the pressure inside your own body when you dive underwater. Descend a few feet into a swimming pool, and you feel the water pressing against your eardrums, gently at first, then more firmly, the deeper you go. And there is no single wall holding that pressure back, no shelf marking where shallow water ends and deep water begins. The pressure simply increases smoothly, with depth, layer folding into layer, without a seam. The sun works on the same basic principle, just at a scale almost impossible to picture, and with pressures at its center that dwarf anything found at the bottom of any ocean on Earth, pressures great enough to compress hydrogen atoms into a stew of bare nuclei and stripped electrons, a state of matter we now call plasma. Plasma is worth pausing on for a moment because it is not quite gas, liquid or solid in the ordinary sense, and it makes up almost the entirety of the sun's visible bulk. At the temperatures found even in the sun's outer regions, temperatures of thousands of degrees, atoms cannot hold on to their electrons the way they do here on Earth. The electrons are stripped away, left to drift freely, leaving behind charged nuclei that also drift freely, the whole substance behaving less like a calm gas and more like a roiling, electrically charged fluid responsive to magnetic fields in ways ordinary matter simply is not. This is part of why the boundary we paused at earlier has no hard edge. Plasma does not sit still the way solid rock does. It churns, it rises, it falls, it thins gradually into the near vacuum of space, rather than stopping abruptly at some fixed wall. So when people speak of the sun's layers, the core, the layers that carry energy outward, the shimmering atmosphere above, it helps to hold those words loosely, the way you might hold the idea of layers in a cup of tea that has just been stirred with milk, distinct in character from one another, distinct in temperature and density and behavior, and yet blending continuously from one into the next, with no true wall separating any of them. Each layer earns its name not because it is physically bounded, but because conditions change enough, gradually, that it becomes useful to give that particular depth its own description, its own chapter in the story. With that balance in mind, gravity pulling inward without pause, pressure and heat pushing outward without pause, the whole vast sphere held in a kind of perpetual, breathing stillness, we can begin our descent in earnest, starting at the very center, the place where all of this begins. If you have ever watched a pot of water just before it reaches a full boil, you will have seen small domes of water rise, hesitate, and sink again, over and over, in a shifting pattern that never quite repeats. Scale that image up by a factor almost too large to picture comfortably, and slow it down until each rising dome takes not a second, but roughly 10 minutes to complete its journey, and you have something close to what the surface of the sun actually looks like when we finally arrive there. This layer is called the photosphere, and the name is well chosen because photosphere simply means sphere of light. It is the depth at which the sun stops being opaque and starts being visible, the place from which the particles of light we call photons can finally travel outward without being absorbed and re-emitted 1,000 times over, the place where, after your long imagined journey from the core, light is at last free to leave. It is worth sitting with that idea for a moment, because it changes what we mean when we say we are looking at the surface of the sun. Earth has a surface in the way you might expect, a place where gas gives way to solid ground, a boundary you could stand on. The sun has nothing of the kind. What we call its surface is not a place where matter changes state or stops. It is a depth, a specific distance from the center, at which the plasma above becomes thin enough that photons passing through it have a real chance of escaping into space, rather than being caught again by some nearby particle. Go a little deeper than this depth, and the plasma is still dense enough to trap light, scattering it, absorbing it, sending it back the way it came. Go a little higher, and the plasma is thin enough that light passes through freely. The photosphere is simply the layer where that balance tips, the last place light can be reliably stopped, and so it is the last place our eyes, or any instrument sensitive to visible light, can meaningfully see. This is a strange thing to hold in your mind as you drift toward sleep, that the visible face of our nearest star is not a solid thing at all, but a threshold, a kind of horizon of visibility, hanging in the middle of a gas that has no true edge. The photosphere is only a few hundred kilometers thick, which sounds substantial until you remember that the sun's radius runs to hundreds of thousands of kilometers. In proportion, this layer of light is thinner than the skin of an apple relative to the fruit inside it. And yet within that thin skin, almost all of the light that warms our planet, that once illuminated the pages of every book ever read by candle or lamp or sun through a window, finds its origin. Beneath this skin, the churning we spoke of earlier
expresses itself in a pattern astronomers call granulation, and it is here that the boiling water image becomes almost literal. Hot plasma rises from below in individual cells, each one perhaps 1,000 kilometers across, roughly the distance from one end of a mid-sized country to the other, though on the sun's scale that counts as modest. At the center of each cell, plasma that has carried heat up from deeper layers breaks the surface, glowing brighter because it is hotter, before cooling slightly, darkening slightly, and sinking back down again at the cell's edges to be reheated and rise once more. The result, seen through a solar telescope, resembles nothing so much as the surface of a pot of simmering porridge, or the mottled skin of an orange. Thousands of these granules, covering the visible face of the sun at any given moment, each one living out its slow rise and fall in about 10 minutes, before dissolving and reforming as a slightly different shape nearby. No granule is permanent. The whole surface is a mosaic that is constantly, quietly, rewriting itself. This restlessness was hidden from humanity for nearly all of its history, not because people failed to look at the sun, but because looking directly at it does such swift and serious harm to the eye that direct observation was, for most of that history, both rare and dangerous. It took the refinement of the telescope, and crucially, the discovery of ways to project the sun's image safely onto a screen, rather than stare at it directly, for astronomers in the early 17th century to begin recording features on its face in careful detail. Among the first to do this systematically was the English astronomer Thomas Harriot, and shortly after him, working independently in different parts of Europe, Galileo Galilei in Italy, and Christoph Scheiner in Germany, both turned their instruments toward the sun and began sketching what they saw, dark blemishes scattered unevenly across its glowing disk. These were sunspots, and their very existence was mildly scandalous at the time, because a sun with blemishes did not sit comfortably with older ideas of the heavens as perfect and unchanging. We now understand sunspots as regions where the sun's magnetic field, which we will explore properly in a later part of this journey, becomes so concentrated and so tangled that it suppresses the normal churning motion of the plasma beneath it. Where that churning is suppressed, less hot material rises to the surface from below, and so the region cools, by solar standards at least, dropping from a typical surface temperature of about 5,500 degrees Celsius to something closer to 3,700 degrees. That is still far hotter than any flame you have ever stood near, but next to the blazing plasma surrounding it, a sunspot appears dark, the way a candle flame can look dim as ash if you photograph it against the noon sky. Sunspots are not holes, and they are not cold in any ordinary sense. They are simply cooler by contrast, patches of restrained brightness on a face that is, everywhere else, almost unbearably bright. The number of these spots rises and falls over a cycle of roughly 11 years, a rhythm first noticed in the middle of the 19th century by a German pharmacist and amateur astronomer named Heinrich Schwabe, who had originally been searching for a hypothetical planet inside the orbit of Mercury, and instead, after 17 years of patient daily sketching, stumbled onto a pattern in the spots themselves. It is a gentle reminder that some of the most important discoveries in the study of our star came not from grand observatories, but from ordinary people willing to look carefully and repeatedly at something everyone else assumed had already been fully seen. If you were able to look at the photosphere edge to edge, rather than only at its center, you would notice something else, subtler than the spots but just as telling. The sun does not appear evenly bright across its disk. Its center glows more fiercely than its edges, an effect called limb darkening, and it arises directly from the same idea we have been circling, that the visible surface is a depth rather than a wall. When you look at the center of the sun's disk, you are looking straight down into the plasma, and your line of sight reaches slightly deeper, hotter layers before the light manages to escape. When you look toward the edge, toward what astronomers call the limb, your line of sight is angled, skimming through the atmosphere at a slant, and so it reaches only shallower, slightly cooler layers before light can escape toward your eye. Cooler plasma glows less brightly, and so the edges appear dimmer than the center, not because anything is truly missing there, but because you are seeing a different depth, and depth on the sun always means temperature. There is one more quiet clue hidden in this light, one that took the careful eyes of a German optician and lens maker to first notice properly. In the early 1800s, Joseph von Fraunhofer, working to perfect the glass for his optical instruments, passed sunlight through a narrow slit in a prism, and found that the resulting rainbow was not smooth and continuous as expected, but crossed by hundreds of thin dark lines, each at its own precise position. These lines, later understood to be the fingerprints of specific elements absorbing specific colors of light as it passed through the cooler gas just above the photosphere, would eventually let scientists determine, without ever leaving Earth, exactly which elements make up the outer layers of a star, 93 million miles away. It is through lines like these that we first learned the sun is overwhelmingly hydrogen and helium, and it is to that thin, revealing layer just above the surface of light that we can now turn our attention.
Let's leave the surface behind for a moment and sink back downward, back into the body of the sun, because before light escapes into space, it has to travel through one final layer, and that layer moves in a way unlike anything below it. This is the convection zone, the outermost of the sun's great interior regions, and it begins roughly 70% of the way out from the center, forming a shell, perhaps 125,000 miles thick. It sounds simple when described quickly. Hot plasma rises, cool plasma sinks. But sit with that idea for a while, slowly, the way you might watch a pot of water just before it boils, and it becomes one of the more beautiful mechanical facts about the star that keeps us alive. Beneath the convection zone, heat moves outward, the way it does through a metal spoon left in a flame, by radiation, photon by photon, each particle of light absorbed and re-emitted countless times, drifting outward with almost unbearable slowness. We touched on that earlier, that a photon, born near the sun's core, can wander for tens of thousands of years, bumping through the dense plasma like someone feeling their way through a crowded room in the dark. But at a certain depth, that method of moving heat stops working efficiently. The plasma there becomes less transparent to radiation, thick with atoms that are not fully stripped of their electrons, atoms that grab photons and hold on to them rather than passing them smoothly along. Heat begins to back up, the way traffic backs up when a wide highway narrows into a single lane. And when heat cannot escape fast enough through radiation alone, nature reaches for a different tool. It starts moving heat through bulk motion instead, through the physical rising and sinking of the material itself. This is convection, and it is the same basic process you can watch in a pot of water on a stove, or in the shimmering air above a sun-baked road, or in the towering shapes of thunderclouds building on a summer afternoon. Except here, it is happening on a scale that would swallow the Earth many times over without slowing down. Picture a parcel of plasma near the base of this zone, heated from below, slightly less dense than the material surrounding it. Because it is lighter, it begins to rise, buoyant in the same simple way a warm air bubble is buoyant in a cooler room.
As it climbs, it carries its heat with it, moving upward through the surrounding plasma, the way a hot air balloon lifts through cooler evening air. It expands as it rises, because the pressure around it drops the farther out it travels, and expanding plasma cools a little. The same way air from a bicycle pump feels cool against your hand as it rushes out and expands. Eventually, this rising parcel reaches a point near the visible surface where it has cooled enough and lost enough of its buoyancy that it can rise no further. There, it spreads out, releases its heat into the thin outer layers, and having given up its warmth, becomes denser than its surroundings once more. Now heavier, it sinks back down, slipping downward along the edges of its former path, plunging back into the depths, to be reheated and to rise again. This endless cycling, rising, spreading, cooling, sinking, reheating, is happening not just once, but in an almost uncountable number of individual cells, side by side, all across the sun, all the time. We can actually see the tops of these rising cells, or at least the largest and nearest of them, in a pattern called granulation. If you looked at the photosphere through a well-built solar telescope on a day of unusually steady air, the surface would resolve not into a smooth glowing sheet, but into something closer to the surface of a pot of simmering oatmeal, or the texture of a well-kneaded orange peel, covered in irregular polygonal cells, each one brighter, in the center where hot plasma is welling upward, and darker along its edges, where cooler plasma is sinking back down. Each of these granules is typically around 600 miles across, which sounds enormous until you remember the sun itself, and then it starts to seem almost delicate, almost fine-grained, like the pattern of foam on the surface of a cappuccino, compared to the size of the cup. And these granules do not sit still. Each one lives for perhaps 8 to 20 minutes before it is replaced by a new one, the whole surface constantly renewing itself, boiling gently, in extremely slow motion, when you consider the size of the structures involved, but with a kind of restless, ceaseless energy, if you could watch it sped up. There is a second, much larger pattern, layered beneath this one, called supergranulation, first identified through careful, patient observation in the 1950s by the British astronomer Richard Woolley, and, independently and more thoroughly, by later researchers using the young science of studying motion in the sun's plasma through shifts in its light. Supergranules are enormous compared to ordinary granules, often 20,000 miles or more across, and they last not for minutes, but for roughly a day or two before dissolving and reforming elsewhere.
Astronomers believe these represent a deeper, larger-scale layer of convective cells, sitting further down in the convection zone, whose motions gently organize and herd the smaller granules above them, the way a slow, wide ocean current can carry along a whole scattered raft of smaller ripples and eddies riding on its surface. Beneath even these, some researchers have proposed the existence of still larger, still deeper, convective structures, sometimes called giant cells, though these remain far harder to observe directly and are still an active and somewhat unsettled area of study. It is worth sitting with that honestly, here in the quiet, that not every layer of the sun's churning has been mapped with certainty, that even now, patient scientists are still arguing gently over data,
still refining what these deep patterns of rising and sinking really look like. All of this churning motion does something else, too, something that connects directly to the puzzle we touched on earlier, the strange behavior of sunspots and the tangled magnetic field.
The convection zone is not just carrying heat outward. It is also dragging plasma, and because that plasma is ionized, stripped of some of its electrons, and therefore electrically charged, its motion drags magnetic field lines along with it, twisting and stretching and knotting them the way slow currents in a river will twist and stretch a long ribbon caught in the water. This churning, combined with the sun's rotation, is part of what is believed to generate and sustain the sun's magnetic field in the first place, a process astronomers call the solar dynamo, though we will return to that idea more fully later, because it deserves unhurried attention of its own. And rotation itself adds one more layer of strangeness to this picture, because the sun does not rotate as a single solid body the way the Earth does. Instead, it rotates differently at different latitudes, a phenomenon called differential rotation. Near its equator, the sun completes a full rotation in about 25 days. Nearer its poles, a full rotation takes closer to 35 days, the plasma there lagging noticeably behind. This alone is a strange thing to picture, a sphere where the middle spins faster than the top and bottom, something no solid object could ever do without tearing itself apart. But the sun is not solid, and its layers are free to slide against one another, gas and plasma, rather than rock and metal. Deep helioseismology, the study of the sun's interior through the sound waves that ripple constantly through its body, waves generated by all this convective churning, bouncing, and echoing inside the sun, the way sound bounces inside a struck bell, has shown that this differential rotation is not just a surface phenomenon. It persists down through much of the convection zone, layer sliding against layer, before giving way, deeper still, to something quite different, a boundary where the whole character of the sun's rotation and its inner structure changes rather abruptly. It is toward that boundary, that quiet, hidden seam inside the sun, that our slow descent will carry us next. So let us settle there for a while, at that seam, because it rewards patience more than almost any other layer we will visit. The boundary is called the tachocline, and if you have never heard the word before, you can let it sit in your mind the way you might let a stone sit in your palm, turning it slowly. It comes from the Greek for speed, tacho, joined to the idea of an inclined boundary, cline, and together the word describes exactly what physicists found there, a shear layer, a place where the smooth, gradual differences in rotation speed that define the convection zone above suddenly sharpen into something much more abrupt, like a slow, wide river narrowing into rapids over a short stretch of rock. Above the tachocline, remember, the sun rotates differentially, the equator outpacing the poles, layer sliding against layer in a soft, continuous gradient, the way currents at different depths in the ocean can drift at slightly different speeds without any hard line dividing them. But below the tachocline, in the radiative zone we described earlier, the sun rotates almost as a single solid body, more or less the same rate from equator to pole, the way the Earth turns, one unbroken motion carrying every latitude around together. So somewhere between these two behaviors, the sliding gas above and the near-rigid turning below, there has to be a transition, and helioseismology, that patient, decades-long project of listening to the sun's internal vibrations, has located it. It sits at roughly 70% of the way from the center to the surface, a thin shell, thin by the sun's standards at least, perhaps only a few percent of the solar radius in thickness, and yet it is thought to be one of the most consequential regions in the entire star. Consequential, because shear is where magnetic fields get organized. Picture, if it helps you drift, a lazy pot of honey, and imagine dragging a spoon slowly through only the top half of it, while the bottom half stays still. Where those two layers meet, the honey does not glide past itself gently. It stretches, it smears. Anything embedded in that boundary, a thread, a strand of something suspended in the honey, would get pulled long and thin, wound tighter and tighter, the longer the dragging continued. Inside the sun, the tachocline is thought to do something similar to magnetic field lines. Weaker, more tangled fields drifting down from the convection zone above meet the shearing motion at this boundary and get stretched out, wound around the sun's rotation axis, amplified, the way winding a rubber band around your finger over and over tightens and thickens the loop with each turn. Many solar physicists suspect that this stretching and winding at the tachocline is a central engine, perhaps the central engine, of the solar dynamo, that broader process mentioned before, which is believed to generate and continually renew the sun's magnetic field. I want to be careful here, gently careful, because this is a place where popular explanations often speak with more confidence than the science itself currently earns. The solar dynamo is one of the most actively studied open problems in all of astrophysics, not because nobody has any idea how it works, but because there are several plausible mechanisms tested against different pieces of evidence, and researchers have not yet agreed on exactly how much of the credit belongs to the tachocline itself versus other dynamo processes operating nearer the surface, within the convection zone. Some models place the primary field generation right at that shear boundary we have been describing. Other models suggest a more distributed process, magnetic amplification happening throughout the convection zone, with the tachocline playing an important but supporting role rather than being the sole engine. What is well established, what has been observed and measured and confirmed many times over, is that the sun's magnetic field does behave in a strikingly cyclical way, and that this cycle is tied to rotation, to convection, and to the shearing motions somewhere inside the star. The precise machinery, the full wiring diagram, is still being worked out, and it is worth resting easy in that uncertainty rather than rushing past it, because honest not knowing is itself a kind of interesting fact about the universe. Now, what is this cycle we keep circling around? If you were to track the number of dark blemishes on the sun's visible surface, the sunspots, over many years, you would notice something almost rhythmic. Sunspots are regions where bundled, concentrated magnetic field lines poke up through the surface, and where they do, they interfere with the normal outward flow of heat from below, so that patch of surface glows a little cooler, and therefore a little darker than the plasma surrounding it, though still, it is worth remembering, blazingly bright compared to almost anything you have ever seen with your own eyes. A large sunspot might be several times the size of the Earth, and the number of these spots visible on the sun rises and falls in a cycle lasting roughly 11 years, a pattern first noticed carefully in the 1840s by a German apothecary and amateur astronomer named Samuel Heinrich Schwabe, who had originally set out looking for a hypothetical planet orbiting inside Mercury's orbit, and instead, after patiently sketching the sun nearly every clear day for over a decade,
stumbled onto this deeper rhythm in the sunspot record instead, a lovely example of how careful, patient observation sometimes hands you a discovery you were not even looking for.
That 11-year rhythm, the sunspot cycle, is now understood to be the visible surface expression of the solar dynamo's underlying magnetic cycle, though the full magnetic cycle is actually about 22 years long, because the sun's global magnetic polarity, its overall north and south magnetic orientation, flips at the peak of each 11-year sunspot cycle and only returns to its original orientation after 2 of those cycles have passed. At the quiet end of a cycle, called solar minimum, the sun's surface can go remarkably calm, sometimes weeks passing without a single visible spot. Then, gradually, spots begin reappearing, first at higher solar latitudes, then drifting closer to the equator as the cycle builds toward its noisy peak, called solar maximum, before quieting again. This latitude drift, plotted over many cycles, produces a pattern astronomers nicknamed the butterfly diagram, because the spreading, wing-shaped bands of sunspot activity, traced out year after year, genuinely do resemble a butterfly's wings opening and closing, cycle after cycle, a strange and lovely bit of order emerging from something as turbulent as a star. And where there are sunspots, and the twisted, knotted magnetic fields that create them, there is also the possibility of far more dramatic events. A solar flare is a sudden, brilliant release of energy, thought to occur when magnetic field lines near a sunspot group become so tangled, so wound up by all that stretching and shearing we have been describing, that they can no longer hold their configuration. Something gives way. The field lines snap and reconnect into a simpler shape, and in that reorganization, magnetic energy that had been stored up, sometimes over days, gets converted almost instantly into light and heat and accelerated particles, a burst that can, in the largest cases, briefly outshine a significant fraction of the entire sun's light output at certain wavelengths. It is a bit like bending a wire coat hanger back and forth, feeling it grow warm under your fingers from all that stored mechanical stress, except imagine the wire finally snapping, all that stress releasing in one sudden instant rather than slowly as heat. Sometimes, though not always, a flare is accompanied by something even larger in scale, a coronal mass ejection, in which an enormous bubble of magnetized plasma, sometimes billions of tons of solar material, gets flung outward from the sun's outer atmosphere entirely, escaping into space at speeds that can reach several million miles per hour. If such a cloud happens to be aimed toward Earth, and this does happen with some regularity, it can take anywhere from about 1 to 3 days to cross the 93 million miles between us, arriving eventually to interact with our own planet's magnetic field, an interaction responsible, among other things, for some of the most beautiful auroras ever recorded in human history. All of this, the flares, the ejections, the 11-year rhythm, the very existence of sunspots at all, traces back to that quiet, shearing seam we paused at earlier, the tachocline, still turning steadily in the dark, still winding its slow, invisible threads, far below the surface where all this visible drama eventually breaks into light. Let's leave the surface behind now, and the shearing and the sunspots and the flares, and travel back inward, down through layers of the sun we have not yet visited, to a region so vast and so strange that it deserves its own quiet stretch of attention. This is the radiative zone, and if you could somehow shrink yourself down and drift into it, you would find yourself in one of the densest, most crowded environments imaginable, a place where energy takes almost unimaginably long to cross what is, in cosmic terms, a fairly short distance. The radiative zone begins just outside the core, roughly a quarter of the way out from the sun's center, and it extends outward until it reaches about 70% of the way to the surface. Within it lives plasma so dense, so tightly packed with charged particles, that light itself, the very thing we associate with speed, with near instantaneous travel, becomes almost trapped. To understand why, we need to go back to where all this energy actually comes from, deep in the core, where hydrogen nuclei fuse together into helium and release, in that process, tiny bursts of pure energy in the form of gamma-ray photons. Each of these photons is born with tremendous energy, and each one begins its journey outward, carrying a small piece of the sun's total light output, the light that will, eventually, billions of years from now, reach your eyes as sunlight. But that journey is nothing like a beam of light crossing an empty room. In the emptiness of space, a photon travels in a perfectly straight line at the speed of light, uninterrupted, arriving at its destination almost instantly, at least on human timescales. In the radiative zone, though, the plasma is so dense that a photon cannot travel more than an extremely short distance before it collides with something, typically an electron, and gets absorbed. When it is absorbed, it does not simply keep going. It disappears, in a sense, and its energy is very briefly held by the particle that absorbed it, before being re-emitted, almost immediately, as a new photon, one usually with slightly different energy, and, crucially, sent off in a completely random new direction. Picture, if it helps, a crowded ballroom, an old-fashioned dance hall, filled wall-to-wall with people, so packed together that you can barely see more than an arm's length in any direction. Now imagine trying to walk from one side of that ballroom to the other in a straight line. You cannot. Every few steps you bump into someone, and each time you do, you are jostled, turned, sent off in some new and unpredictable direction, sometimes back the way you came, sometimes sideways, only occasionally, continuing usefully forward. This is roughly what happens to a photon in the radiative zone, except the collisions happen not every few steps but after traveling something like a single centimeter, sometimes less, before being absorbed and re-emitted yet again, in yet another random direction. This kind of motion, where each step is random and independent of the ones before it, has a name in physics and mathematics. It is called a random walk, and it has a peculiar and somewhat counterintuitive property. You might think that if each step covers, say, 1 centimeter, then after enough steps a photon should have wandered fairly far from where it started, simply by accumulating distance. But a random walk does not accumulate distance efficiently at all, because so many of those steps cancel each other out. Moving 1 centimeter forward, then 1 centimeter back, then 1 centimeter sideways, leaves you very close to where you began, even though you have technically traveled 3 centimeters worth of steps. The net progress, the actual displacement from the starting point, grows only with the square root of the number of steps taken, not in direct proportion to them. This means that to travel a meaningful distance, the number of individual steps required becomes astronomically large. Apply this to the radiative zone, which stretches for hundreds of thousands of kilometers, and the numbers become almost impossible to hold in the mind. Estimates vary, and this is genuinely difficult to calculate with precision, depending on assumptions about density and temperature at each depth. But many estimates suggest that the effective time for energy to random walk its way from the core, through the radiative zone, could be on the order of tens of thousands of years, and some calculations, depending on the exact model used, push that figure even higher, toward 100,000 years or more. There was a period, incidentally, in the 20th century, when physicists debated this quite seriously, refining their understanding of solar opacity.
of exactly how effectively the plasma scatters and absorbs photons at different depths, because getting this number right matters enormously for understanding how the sun works as a whole, how long it takes for energy generated today, this very moment, in the fusing core, to finally reach the surface and radiate away as the sunlight we depend on. Here, though, is where an important distinction becomes necessary, one that often gets blurred in casual explanations, and one worth sitting with for a moment, because it resolves what might otherwise feel like a puzzling contradiction. When we say a photon takes tens of thousands of years to cross the radiative zone, we are not saying that a single photon born in the core survives, intact and unchanged, for all that time, patiently making its way outward, like a very slow traveler on a very long road. That is not what happens at all. That original gamma-ray photon is absorbed and destroyed almost immediately, within a tiny fraction of a second of being created, and a new photon takes its place, one with less energy, because some of that energy was passed to the surrounding plasma in the process. This happens again, and again, an almost incomprehensible number of times, each individual photon existing only briefly, before being absorbed and replaced by another. So it is not the photon itself that makes this long, slow journey. It is the energy, passed along like a whispered message relayed from person to person, down an enormously long line, where each person hears the message, forgets the exact words, and passes on their own rough approximation to the next. The specific photons change constantly, are born and destroyed constantly, but the energy itself, in aggregate, slowly diffuses outward, seeping through the dense plasma the way heat seeps through a thick metal bar, or the way a drop of ink, released into perfectly still water, spreads outward, not because any single ink molecule races across the container, but because countless random collisions gradually carry the color, on average, away from where it started.
This process, energy transport by radiation, by the repeated absorption and re-emission of light, works well enough in the radiative zone because the plasma there, while dense, is arranged in fairly stable, calm layers, without much churning or bulk movement of material. The temperature decreases gradually as you move outward, from around 15 million degrees Celsius near the core boundary down to a few million degrees by the time you approach the outer edge of this zone, and that gradual temperature gradient is gentle enough, given the plasma's particular properties at these depths, that radiation alone can carry the energy along without the material itself needing to physically move. Scientists sometimes describe this using the concept of opacity, a measure of how difficult it is for light to pass through a given material without being absorbed or scattered. The radiative zone has enormously high opacity, particularly in its lower, denser regions, which is precisely why photons struggle so much to make headway there, why each step in that long random walk is so short, so easily undone by the very next collision. It is worth pausing, here in the quiet, dense dark of this zone, to appreciate just how strange this really is. The sunlight warming your skin on some afternoon, whenever you next feel it, began its existence as a gamma ray in the sun's core, and then spent an almost unfathomable stretch of time, possibly longer than the entire span of recorded human civilization many times over, simply trying to find its way outward through a few 100,000 kilometers of dense, scattering plasma, absorbed and reborn over and over, drifting only slightly closer to the surface with each new incarnation. And even once that energy finally approaches the outer boundary of this radiative zone, its journey is still far from finished, because the conditions there begin to change in a way that will alter, quite dramatically, how energy makes the rest of its way outward. Let us go back, for a while, to that innermost region we spoke of earlier, and sit with it a little longer, because the core of the sun deserves more patience than a passing glance. It is, after all, the reason everything else exists the way it does. The radiative zone, the convective zone above it, the shimmering surface we call the photosphere, all of it is downstream, in a sense, of what happens in that small, almost unimaginably dense sphere at the very center. So let us slow down and sit inside it for a while, the way you might sit in a warm room in winter, simply noticing. The core of the sun occupies only a small fraction of its total volume, perhaps a quarter of the radius. Yet within that modest sphere is packed nearly half of the sun's entire mass. Picture that for a moment. Half of everything the sun is, squeezed into a region that relative to the whole star is barely more than a kernel inside a fruit. This is not a gentle packing. It is a packing achieved only because of the staggering weight of everything above pressing down, layer upon layer, for 4.5 billion years and counting. At the very center, the temperature reaches somewhere around 15 million degrees Celsius. Numbers like this are easy to say and difficult to actually feel, so let us try, gently, to get some sense of what such a temperature means. On Earth, the hottest industrial furnaces, the ones used to forge steel or melt tungsten, reach perhaps 3,000 or 4,000 degrees. The surface of the sun itself, that visible yellow-white disk we are told never to look at directly, is around 5,500 degrees. The core is nearly 3,000 times hotter than that surface. At these temperatures, nothing resembling the matter we know on Earth can exist. There are no molecules. There are not even ordinary atoms in the way we usually picture them, with a tidy nucleus and its cloud of orbiting electrons. The heat is so extreme that electrons are stripped entirely away from their nuclei, torn loose by the sheer violence of thermal motion, leaving behind a state of matter known as fully ionized plasma. It may help to think of an atom in cooler and calmer conditions as something like a tiny solar system in miniature, a nucleus at the center with electrons circling around it, held in place by electrical attraction. In the sun's core, that arrangement is simply impossible to maintain. The particles are moving and colliding so violently, so constantly, that any electron trying to settle into an orbit around a nucleus is knocked loose again almost instantly. What remains, then, is not atoms in the familiar sense, but a churning sea of bare atomic nuclei, mostly hydrogen nuclei, which is to say, single protons mixed together with a great swarm of free electrons, all of it electrically charged, all of it in constant, frantic motion. This is plasma, sometimes called the fourth state of matter, distinct from solid, liquid, and gas, and it behaves according to its own particular rules, since it responds not only to pressure and temperature, but to electric and magnetic forces as well. Now, alongside this almost incomprehensible heat, sits an equally almost incomprehensible density. It is worth noting that the core's density does not come from the plasma being cold or slow-moving, since heat, in a sense, works to expand things and push them apart. Rather, the density comes from the sheer weight of the material above, hundreds of thousands of kilometers of solar plasma, all of it under the pull of gravity, all of it pressing down and inward toward the center. The result is that matter in the core is compressed
to roughly 150 times the density of water. Water, as you may remember filling a glass or watching rain collect in a puddle, has a certain ordinary heaviness to it, a liter of it weighing a kilogram. Now imagine that same liter of material, compressed until it weighs 150 kilograms, as much as a large adult person, and squeezed into that same small space. That is roughly the density of matter at the sun's very heart, and it is denser, remarkably, than lead, denser than iron, denser than nearly anything solid we might handle here on Earth, and yet it remains, in the technical sense, a gas, or more precisely a plasma, simply because it is far too hot to condense into anything resembling a liquid or solid. This combination, extraordinary heat, paired with extraordinary density, creates conditions of pressure that are similarly difficult to hold in the mind. Estimates suggest the pressure at the sun's core reaches something in the range of 250 billion times the atmospheric pressure we experience here at Earth's surface, the pressure that quietly presses on your body right now as you rest and listen. If you have ever felt your ears pop while diving to the bottom of a swimming pool, or felt the mounting pressure descending in an airplane, you have some small taste, though only the faintest whisper, of what pressure feels like as it increases with depth. The core of the sun exists under a kind of crushing confinement that has no real equivalent in ordinary human experience, sustained moment after moment, day after day, by the unrelenting weight of the entire star pressing down from every side. It is this pressure, this deep confinement, that makes fusion possible at all, and here is where something rather beautiful and slightly strange enters the picture. Even at 15 million degrees, even under 250 billion atmospheres of pressure, the hydrogen nuclei in the sun's core are not, on average, moving quite fast enough to overcome the electrical repulsion between them and collide the way fusion requires. Two protons, both positively charged, resist coming close together, pushing against one another the way two magnets with matching poles resist being pressed face to face. Classical physics, the physics of everyday billiard balls and moving cars, would suggest that most collisions in the sun's core should simply bounce apart, repelled before they ever truly meet. And yet fusion happens, reliably, constantly, has been happening for billions of years. The explanation lies in a curious and thoroughly well-established feature of quantum mechanics called tunneling. At the scale of subatomic particles, the sharp boundaries and definite positions we take for granted in daily life begin to blur. A proton does not exist at one single precise point the way a marble does when it comes to rest on a table. Instead, it exists as a kind of probability, spread out over a small but real range of possible positions, described by a wave function that tells us, roughly, how likely it is to be found in any given place. Because of this blurring, there is a small but genuine chance that two protons, even without quite enough energy to smash through the electrical barrier between them, in the classical sense, will simply find themselves, quantum mechanically, on the other side of that barrier, as though they had slipped through a wall, rather than climbed over it. This is quantum tunneling, and without it, the sun's core, despite its heat, would not generate nearly enough fusion to shine. It is a delicate process even so. On any given day, the vast majority of protons in the core do not fuse. The odds for any individual pair of protons meeting under just the right conditions to tunnel through that barrier are exceedingly small, and it is really only the staggering number of protons present and the staggering number of collisions occurring every single second that makes fusion happen often enough, cumulatively, to power an entire star. It has been estimated that an individual proton in the sun's core might wait, on average, several billion years before finally fusing with another. It is a slow, patient, statistical process, playing out across an almost unfathomable number of particles, and it proceeds so gently, in fact, that the sun releases energy at a rate, per unit of volume in its core, that is actually less than the metabolic rate of a resting human body.
The sun shines not because its core is furiously, violently reactive in any single spot, but because it is so enormous, containing so much material, that even this quiet, gradual process adds up to something vast. All of this rests upon a balance, and it is worth dwelling on that balance for a moment before moving forward, because it is really the central fact holding the whole star together. Gravity is always pulling inward, always trying to compress the sun further, to collapse it down toward its center. Working against that pull is the outward pressure generated by all this heat, this fusion, this frantic thermal motion of plasma trying to expand. For 4.5 billion years, these two forces have remained in almost perfect balance, an equilibrium so precise that the sun neither collapses under its own weight nor blows itself apart into space. It is this quiet standoff, this long stalemate between crushing gravity and searing heat, that has allowed the sun to burn so steadily for so long, and it is worth turning next to how that balance actually plays out, moment to moment, deep inside the core. Let's follow one of those patient protons all the way through, since we now understand why it waits so long, and see what actually happens in the rare moment it finally succeeds. Picture two protons, finally close enough, finally slow enough, finally lucky enough to tunnel through that electric barrier we described earlier. For a fleeting instant, they touch, and in that instant, something remarkable happens, something that could never occur under ordinary circumstances anywhere on Earth. One of the two protons transforms. It does not simply stick to its partner the way two magnets might click together. Instead, through the workings of what physicists call the weak nuclear force, one proton converts into a neutron, right there in the collision. This is the first step of what is known as the proton-proton chain, and it is worth sitting with how strange this transformation really is. A particle that was positively charged, a proton, becomes a particle with no charge at all, a neutron. Charge cannot simply vanish, though, so something must carry that positive charge away. And that something is a new particle altogether, a positron, which is essentially the antimatter twin of an electron, identical in nearly every way except that it carries a positive charge instead of a negative one. Alongside that positron, another particle slips out of the reaction, one so strange and so elusive that it deserves a moment of its own. This is the neutrino. Neutrinos have no charge and vanishingly little mass, so little that for decades physicists debated whether they had any mass at all. They interact with matter so weakly that they can pass through the entire sun, through the earth, through you, lying there right now, without so much as touching another particle. Trillions of them are streaming through your body in this very moment, products of these same fusion reactions happening deep in the sun's core 8 minutes ago, and you will never feel a single one. It is a strange thought to rest with as you drift toward sleep, that you are, quite literally, bathed in the ghostly aftermath of the sun's inner workings, threaded through by particles born in nuclear reactions and gone again before you could ever notice them. So, from that first proton-proton collision, we now have a neutron and a proton bound together, along with a positron and a neutrino that go their own separate ways.
that neutron and proton, joined together, form what is called a deuteron, which is simply a heavier, rarer version of hydrogen, one that carries an extra neutron in its nucleus. This deuteron does not remain alone for long. Almost immediately, in cosmic terms, it collides with yet another proton drifting through the crowded plasma. This time, no transformation is needed. The proton simply joins the deuteron, fusing with it to form a nucleus made of 2 protons and 1 neutron. This combination is a light form of helium, sometimes called helium-3, distinct from the more familiar helium-4 that fills party balloons here on Earth. This step in the chain happens quickly and easily compared to the first step, since it does not require that improbable transformation of a proton into a neutron. It is, in a sense, the easy part of a very difficult journey. Now here is where the process becomes patient again, waiting for its final act. 2 of these helium-3 nuclei, each one having taken its own separate, achingly slow path through the first 2 steps, must eventually find each other and collide. When they do, something elegant happens. They merge, briefly forming an unstable nucleus, and then that nucleus sheds 2 of its protons, spitting them back out into the plasma to begin the long, patient journey all over again. What remains, once those 2 protons are released, is a nucleus with 2 protons and 2 neutrons bound tightly together. This is ordinary helium, helium-4, the same stable, common form of helium that makes balloons float and that giggles turn squeaky when inhaled. It is one of the most tightly bound, most stable arrangements of nuclear matter that exists anywhere in the universe, and it is the true, final product of the proton-proton chain.
If you step back and count everything that went into this whole sequence, from the very first collision to the very last, you find that it took 4 individual protons, 4 separate hydrogen nuclei, to ultimately build 1 nucleus of helium-4. Along the way, 2 of those original protons were briefly converted into neutrons and back into protons again through their intermediate steps. 2 positrons were released, 2 neutrinos went streaming off into space, and a certain amount of energy was set free as well, in the form of gamma rays, those most energetic particles of light. This is really the heart of solar fusion. 4 hydrogens go in. 1 helium comes out, along with light and these strange, nearly weightless messenger particles. Now here is the part that connects everything back to that famous idea of Einstein's, the equivalence of mass and energy, and it is worth slowing down for, because it explains, in the most literal sense, why the sun shines at all. If you were to carefully weigh 4 individual hydrogen nuclei, and then weigh the single helium-4 nucleus that results from fusing them together, you would discover something curious. The helium nucleus weighs very slightly less than the sum of the 4 hydrogen nuclei that went into making it. Not by much, only about 0.7% of the total mass, but that missing mass has not simply disappeared. It has been converted directly into energy, following that famous relationship where energy equals mass multiplied by the speed of light squared, a number so large that even this tiny fraction of mass, when converted, yields an extraordinary amount of energy. It can help to imagine this on a very small, very human scale, purely to get a feel for the proportions involved, since the actual numbers are almost impossible to hold in the mind directly. If you could somehow convert just 1 gram of matter entirely into energy, roughly the mass of a paperclip, you would release enough energy to power a fair-sized city for the better part of a day.
The sun, of course, is converting something on the order of 4 million tons of matter into energy every single second. A staggering figure, and yet, spread across a star as vast as the sun, this rate of conversion barely dents its total mass over the course of billions of years. It is a testament to just how much material the sun contains that even this relentless, second-by-second consumption of mass has cost it, so far, only a very small fraction of its overall bulk. And this brings us, gently, to the question of why this whole process unfolds so calmly, why the sun does not simply detonate, given that nuclear reactions, in so many other contexts, are associated with sudden, violent release. The answer lies partly in the very slowness we discussed earlier, that patient waiting of billions of years between one proton's fusion events, and partly in something called a negative feedback loop, a kind of built-in thermostat that keeps the whole system in check. If, for some reason, the fusion rate in the core were to increase even slightly, producing a bit more energy than usual, that extra energy would heat the surrounding plasma. Hot plasma expands, and as it expands, it becomes less dense, spreading its particles further apart. And with particles further apart, collisions become less frequent, which slows the fusion rate right back down again, cooling things off, allowing the plasma to contract once more, and pressure to build back up, until the process gently resumes its usual pace.
It is a self-correcting system, endlessly nudging itself back toward equilibrium, and it is this built-in stability, this natural regulation, that has allowed the sun to burn so evenly for so long, without ever running away into catastrophe. It is a curious thing to realize that the very same physics, capable of producing a hydrogen bomb, an uncontrolled explosive chain reaction, produces instead, inside a star, something closer to a smoldering, self-regulating ember, vast beyond imagining, but calm. And having traced this single, elegant chain from hydrogen all the way to helium, it seems worth turning next to consider just how far that released energy still has to travel, and just how strange and roundabout its journey out of the sun's core truly is. Let's follow one particular messenger from that fusion chain, because not everything born in the sun's core takes the long, patient road outward. Most of the energy released down there travels as light, as photons, and as we'll see, that light has an almost absurdly slow and tangled journey ahead of it, bouncing and scattering through dense plasma for what can be tens of thousands of years before it finally escapes. But alongside those photons, each fusion reaction also produces something else, something far stranger in its behavior, called a neutrino. And unlike the photon, the neutrino does not get stuck. It does not scatter, does not bounce, does not spend millennia jostling through the crowded plasma of the sun's interior. It simply leaves. Almost the instant it is created, deep in the core, it passes outward through the entire body of the sun as though that vast sphere of plasma were barely there at all, and about 8 minutes later, moving at very nearly the speed of light, it reaches the earth and passes through that too, and through you, lying there now, and keeps going, off into space, almost certainly, forever unimpeded. This is worth sitting with for a moment, because it sounds almost too strange to be true. The neutrino is so reluctant to interact with matter that trillions of them are passing through your body every single second, right now, day and night alike, since at night they simply come up through the earth from the sun on the other side, and the earth is no more an obstacle to them than empty space would be. If you wanted to build a wall thick enough to have a decent chance of stopping a single solar neutrino, you would need something on the order of a light year of solid lead. That is not a typo, and it is not an exaggeration for effect. It is simply how astonishingly weak the interaction is between a neutrino and ordinary matter. Neutrinos feel only the weak nuclear force and gravity, for something so close to massless, barely counts at all. This is why they are sometimes called ghost particles, though ghost undersells it, since at least a ghost is imagined to occasionally bump into a wall. And yet, precisely because they interact so rarely, when a neutrino does happen to strike something, it becomes an extraordinarily precious event, a direct message from the sun's core, carried without distortion, without delay, without having been reprocessed or reabsorbed along the way. A photon that reaches your eye tonight left the sun's surface only about 8 minutes ago. True, but the energy it carries was generated in the core, perhaps tens of thousands of years earlier, and by the time it finally escapes, it has been absorbed and re-emitted so many times, in so many different directions, that any direct information about the conditions where it was born has been thoroughly scrambled. The neutrino carries no such scrambling. It is a snapshot, essentially instantaneous, of what is happening in the sun's core at this very moment, or rather, 8 minutes ago, since that is how long the light-speed journey takes, even for something that does not scatter. Scientists in the middle of the 20th century realized that if they could somehow catch a few of these neutrinos, they would have a way of peering directly into the sun's furnace, bypassing entirely the slow, indirect inference that comes from studying sunlight. The trouble, of course, was catching them at all. If a neutrino will pass through a light year of lead without much trouble, how do you build a detector on Earth with any hope of noticing it? The answer, worked out by an American chemist named Raymond Davis Jr., working through the 1960s at the Homestake Gold Mine in South Dakota, was to go deep underground, nearly 1.5 miles down, shielding the detector from the constant rain of other particles, cosmic rays and their secondary showers, that would otherwise drown out any faint neutrino signal. Down there, in the cool dark of the old mine, Davis installed an enormous tank, roughly the size of an Olympic swimming pool, filled with over 300,000 gallons of a common dry cleaning fluid, chosen because it contained a particular form of chlorine. Every so often, on the rarest of occasions, a solar neutrino, passing through the tank, would strike one of those chlorine atoms just right, transforming it into a radioactive form of argon. And then, patiently, periodically, Davis and his collaborators would bubble helium gas through the enormous tank to flush out these vanishingly few argon atoms, sometimes only a handful of them, out of the hundreds of thousands of gallons of fluid, and count them, one by one, using their faint radioactive decay as a signature. It worked, in the sense that neutrinos were indeed detected, confirming that the sun really was powered by nuclear fusion, exactly as theory predicted. But it also produced a genuine puzzle, one that would trouble physicists for decades. Davis's experiment was consistently catching only about 1/3 of the neutrinos that solar models said it should. Not a small discrepancy easily explained away by an instrument that was slightly miscalibrated, but a persistent, stubborn shortfall. Roughly 2/3 of the expected neutrinos simply weren't showing up. This became known as the solar-neutrino problem, and for a long while, nobody was entirely sure where the fault lay. Perhaps the models of the sun's interior were subtly wrong. Perhaps the detector itself had some flaw nobody had yet identified. Perhaps, some physicists began to wonder, almost reluctantly, the neutrinos themselves were doing something nobody yet understood. That last possibility turned out to be correct, and the resolution, when it finally came, revealed something rather beautiful about the nature of these particles. It turns out there are 3 different types, or flavors of neutrino, and the kind produced by the fusion reactions in the Sun's core is only one of them. Davis's detector, tuned specifically to catch that one flavor, was blind to the other 2. And what physicists eventually confirmed, through further experiments in the 1990s, and especially with a large heavy water detector in Sudbury, Canada, capable of catching all 3 flavors rather than just the one, is that neutrinos are not fixed in their identity as they travel. They oscillate, shifting from one flavor to another and back again as they make their journey from the Sun's core out through space to the Earth. By the time they arrive, roughly 2/3 of them have shifted into flavors that Davis's original chlorine tank simply could not see. The neutrinos were never missing at all. They had just changed costume along the way, and it took physicists decades of patient work to realize the detector needed to be looking for all 3 disguises, not just one. It was, in its own quiet way, one of the more satisfying resolutions in the history of physics, and it also revealed something previously unknown, that neutrinos, once thought to be entirely without mass, must actually carry a tiny amount of mass after all, since flavor oscillation of this kind is only possible for particles that do. While neutrinos were offering this one kind of direct glimpse into the Sun's hidden interior, another entirely different technique was quietly developing alongside it, one that listens rather than watches, and it comes from studying the way the Sun's surface gently, rhythmically heaves and settles, over and over, in complex overlapping patterns. This is called helioseismology, and the name is a fair description of what it does, borrowing the logic of earthquake science and turning it toward the Sun. Just as geologists can infer the hidden layered structure of the Earth's interior by studying how seismic waves from an earthquake travel through it, bending and slowing and speeding up as they cross different materials, solar physicists discovered that the Sun's surface is constantly rippling with sound waves, generated by the turbulent boiling motion of plasma just beneath the visible surface, and that these waves travel down into the Sun's interior, bounce off deeper layers, and return, causing the surface itself to oscillate gently, rising and falling by mere kilometers on timescales of minutes. These oscillations can be measured with remarkable precision by watching how light from different points on the Sun's surface shifts very slightly in wavelength as that surface moves toward or away from us, the same Doppler effect that changes the pitch of a passing ambulance siren. And by cataloging millions of these overlapping wave patterns, each one sensitive to different depths and different conditions within the Sun, scientists have been able to build up an extraordinarily detailed picture of the solar interior structure, its temperature and density, and even its rotation at different depths, all without ever needing to physically sample the material itself. It is, in its own way, every bit as indirect and every bit as clever as the neutrino work. 2 entirely different kinds of listening, one to particles that almost never speak, and one to a chorus of sound trapped endlessly rolling within a star, and together they have let scientists confirm, layer by careful layer, that the models of the Sun's hidden furnace were, all along, remarkably close to right. And it is worth pausing now to consider what lies just above that furnace. In the long, slow, radiative expanse, the light itself must still cross,
before it ever reaches the surface at all.
Let it wait there a moment longer, that long, slow expanse of light in transit, because before following a single photon on its journey outward, it helps to step back and ask a simpler question, one that sounds almost childlike in its plainness. How much energy is the sun actually making, right now, in this instant, deep in that core we have been circling for so long? And the answer, once you have it, turns out to connect almost everything we have already wandered through: the fusion reactions, the neutrinos, the trapped light, the seismic ripples, all of it threading back to a single number that astronomers call luminosity. The sun's luminosity is, in essence, the total rate at which it pours energy out into space, across all directions, measured in raw physical terms rather than in how bright it merely looks from Earth. It is an almost unimaginable quantity, and yet it can be pinned down with real precision because satellites orbiting far above our sheltering atmosphere can measure exactly how much solar energy arrives at a given patch of space each second, and from that simple measurement, combined with the well-known distance from the Earth to the Sun, the total output can be calculated the way you might infer the brightness of a lighthouse from how much of its light reaches your boat, once you know how far offshore you are. The result is a figure so large it resists comfortable comparison, though people have tried for centuries, imagining it as some multiple of every power plant humanity has ever built, running without pause, forever. The actual number matters less here than the fact that it can be measured at all, and measured so precisely that even tiny wobbles in it, fractions of a percent, can be tracked over years. What is worth sitting with, in the quiet of this thought, is how that number connects back down into the core, because the fusion reactions happening there, the proton chains merging under crushing pressure that we spent so long describing, are, in aggregate, exactly what generates this outward flow. Every second, an almost incomprehensible number of these fusion events occur, hydrogen becoming helium, a tiny fraction of mass converting into energy, according to that famous relationship between mass and energy that Einstein worked out in the early years of the 20th century, sitting at a patent office desk in Switzerland, long before anyone imagined it would one day explain how stars shine. And when you add up all those tiny individual conversions, all those small losses of mass turned into light and heat, they sum, in total, to match the luminosity we measure from the outside. The core's fusion rate and the sun's brightness are, quite literally, two descriptions of the same underlying process, one measured by inference deep within, the other measured directly with instruments in orbit, and the fact that they agree, once all the physics is worked through, is one of the quiet triumphs of stellar astrophysics. But here a curious tension appears, one that puzzled early researchers and rewards a slow unpacking. If the core is generating energy so ferociously, why does the sun not simply flare up, brighten wildly, and destabilize? Why has it burned so steadily, by all geological evidence, for billions of years, rather than sputtering or surging unpredictably? The answer lies in something astronomers call the thermostat of a star, a self-regulating mechanism built directly into the physics of pressure and temperature, and it is worth turning it over slowly, because it explains why the sun has been, for most practical purposes, a remarkably patient and consistent presence in the sky. Picture the core, for a moment, as existing in a delicate balance between two competing tendencies. Gravity is always pulling inward, trying to compress that dense material further, while the pressure generated by fusion, both the outward push of hot gas and of light itself, is pushing back outward, resisting collapse.
This balance is called hydrostatic equilibrium, and it is remarkably self-correcting. If for some reason the fusion rate in the core were to rise even slightly, the core would generate a bit more energy, which would raise its temperature and pressure, which would cause it to expand very slightly, and that expansion would cool the core down again, because gas that expands generally cools. The same principle at work when air rushes cooled from an aerosol can or a bicycle pump grows warm as it compresses. And with the core cooled by that small expansion, the fusion rate, which depends extraordinarily sensitively on temperature, would drop back down toward its earlier value. The reverse happens too. If fusion should momentarily dip, the core contracts a little under gravity's steady pull, heats back up through that compression, and fusion rates climb again to compensate.
It is a feedback loop operating over impossibly short timescales in the core itself, holding the whole furnace in a kind of trembling, self-correcting stillness, not unlike a person walking a tightrope, constantly making tiny unconscious adjustments, leaning one way and then another, never falling, because the corrections happen faster than any real fall could occur. This thermostat is precisely why the sun has not run away into an uncontrolled explosion, and why it has not sputtered out into darkness either, at least not yet, and not for a very long while still to come. But steady does not mean perfectly unchanging, and this is where the story grows more interesting and considerably slower, unfolding over timescales that dwarf any human frame of reference. As hydrogen in the core is steadily converted into helium, the core's composition itself is changing, and this changes the core's density and the way heat moves through it. And over the enormous span of the sun's life, this has meant a slow, gradual increase in the sun's brightness. Not a sudden one, not something any single human lifetime could register, but real nonetheless. The mechanism is worth walking through gently, because it can feel counterintuitive at first. Helium, being denser than hydrogen for a given number of particles, tends to sink and concentrate near the very center of the core, and as this happens, the core very slowly contracts under its own gravity, and by the same logic as the thermostat we just described, that contraction raises the core's temperature, which in turn increases the rate of fusion reactions, which increases the total luminosity of the star. It is an achingly slow drift, but it is persistent, running continuously across billions of years, so that the sun today shines meaningfully brighter than it did when it first settled into steady hydrogen fusion, back when the solar system itself was still young, and the planets had only recently finished gathering themselves out of swirling debris. This brings us to a genuine puzzle in the history of our solar system, one that scientists have wrestled with since the 1970s, when astrophysicists first worked out with confidence how much dimmer the young sun must have been. Models of stellar evolution suggest that when the Earth was newly formed, some 4.5 billion years ago, the sun was likely somewhere around 70% as luminous as it is today, a substantial difference, enough that, by the simplest calculations, the Earth's oceans should have frozen solid under such a weak, pale sun. And yet the geological record tells a very different story, one written into ancient sedimentary rocks and the chemical traces left behind by early liquid water, showing that Earth had flowing rivers and standing seas, even in that distant, dimmer epoch, rather than a frozen, lifeless shell of ice from pole to pole. This mismatch between a faint young sun and a demonstrably unfrozen young Earth is known, quite plainly, as the faint young sun problem, and it remains, even now, an area of active and genuinely open scientific investigation, rather than a settled matter with one tidy answer. Various explanations have been proposed over the decades,
since the puzzle was first framed, and it is worth mentioning a few, gently, without pretending any single one has been proven beyond doubt.
Some researchers have pointed to a much stronger greenhouse effect on the early Earth, perhaps driven by far higher concentrations of carbon dioxide or methane in the ancient atmosphere, gases that trap heat efficiently enough to have kept the oceans liquid despite the fainter sun overhead. Others have suggested that the young Earth's clouds and surface reflectivity may have differed enough from today's to allow more of that limited sunlight to be absorbed rather than reflected back into space. Still others have looked toward more exotic possibilities, including questions about whether the early sun itself may have behaved slightly differently than the simplest models predict, losing mass through a stronger young stellar wind in ways that could subtly affect its brightness history. No single explanation has become the unanimous consensus, and part of what makes the problem so compelling, even now, is that it sits at the intersection of stellar physics and planetary climate science, two fields that do not always speak the same language, and solving it fully will likely require insights from both. What matters for our purposes here, drifting as we are through the layered anatomy of the sun's interior, is simply this quiet recognition that the star above us is not a fixed, unchanging lamp, but a slowly evolving furnace, brightening by degrees so gradual that no civilization has ever noticed the change directly, and that this same slow brightening, extended forward across billions of years yet to come, will eventually reshape the conditions on Earth in ways far more dramatic than anything in our comfortable present. But that far future can wait a while longer in this telling, because there is still more to understand about the world that light must cross on its way out from the core, the strange, dense, radiative interior lying just beyond the fusing heart of the sun. Let us step back now, further than we have stepped before, far enough that the sun's present moment shrinks to a single frame in a much longer film, a film that began long before there was an Earth to warm, and will continue long after the Earth, in any form we would recognize, has ceased to exist. It helps, drifting here in the quiet interior, to hold the whole arc loosely in mind, not to memorize it, but simply to feel where today sits within it, the way a person might glance at a family photograph and understand, without needing to be told, that the smiling child in the picture is the same person who now, decades later, tells the story of that day. The story begins in cold and darkness, roughly 4.5 billion years ago, in a slowly turning cloud of gas and dust, drifting through a spiral arm of the galaxy, a cloud made mostly of hydrogen, left over from the universe's earliest moments, laced with heavier elements, forged in the deaths of stars that came before. Clouds like this are enormous, spanning distances that would take light years to cross, and for long stretches of time they simply exist, diffuse and unremarkable, until something disturbs them. Perhaps a nearby star exploded, sending a shock wave rippling outward. Perhaps the cloud simply drifted into a denser region of the galaxy and began to compress under its own accumulating gravity. Whatever the trigger, once a pocket of that cloud became dense enough, gravity began to win an old and patient contest against pressure, and the pocket started to collapse inward on itself. That collapse is worth pausing on, because it is not a single dramatic event, but a long, uneven process, one that likely took hundreds of thousands of years, even in its earliest and fastest phase. As the cloud fragment pulled inward, It spun faster, the way a skater's spin quickens when the arms are drawn in close to the body, and it flattened into a disk, with most of the material gathering into a growing, glowing sphere at the center, while the remainder spread out around it. Material that would, in time, become planets, moons, asteroids, and comets. That central sphere grew hotter as it collapsed, not because of any nuclear process yet, but simply because gravitational energy was being converted into heat, the same basic principle that warms your hands when you rub them together, only here, acting on a scale involving a mass more than 300,000 times that of the Earth. This early object is called a protostar, and for a time it shone from the heat of its own contraction alone, glowing dimly, and often hidden behind a thick shroud of the very dust and gas from which it was forming. The protostar continued to contract and heat for perhaps another few tens of millions of years, its core growing steadily denser and hotter, until finally, deep in that center, temperatures climbed past the roughly 10 million degree threshold, where hydrogen nuclei could begin fusing into helium in appreciable numbers. This was the moment, if it can be called a single moment across such a gradual transition, when the sun truly became a star in the sense we use the word today, an object generating its own light not from falling inward, but from nuclear fusion, and specifically settling into what astronomers call the main sequence, a long, comparatively stable phase in which a star fuses hydrogen into helium in its core, at a steady, self-regulating rate. The Sun has now spent roughly the last 4.5 billion years in this phase, and by the estimates most stellar physicists currently favor, it is expected to remain here for perhaps another 5 billion years more, making it, right now, tonight, somewhere close to the midpoint of its main sequence life, neither young nor old for a star of its kind, simply settled into a long and fairly steady middle age. It is worth saying clearly that this stability is not perfect stillness. As we touched on earlier, the sun has been brightening slowly this entire time, its core growing very gradually denser and hotter, as hydrogen is steadily converted into helium, helium being slightly heavier and taking up less space, which causes the core to contract just slightly and heat just slightly, which in turn increases the rate of fusion just slightly. It is a slow ratchet, not a sudden change, and it will continue for the rest of the main sequence phase, but the picture changes more dramatically once the hydrogen fuel in the sun's core is substantially used up, an event that lies something like 5 billion years in the future, a span of time so far beyond any human concern that it can be considered with the same calm curiosity one might bring to a geological fact about a distant continent. When that hydrogen fuel in the core finally runs low, the core will no longer generate enough outward pressure to balance the crushing inward pull of gravity, and it will begin to contract, much as the original protostar once did. That contraction will heat the layers just outside the core, a shell of hydrogen still surrounding the now helium-rich center, hot enough for that shell to ignite in fusion of its own. This shell burning will actually push the sun's outer layers outward and cause the whole star to swell dramatically, cooling as it expands, its surface reddening, and the sun will become what astronomers call a red giant, a star perhaps 100 times larger in radius than it is now, large enough that its outer atmosphere may extend out past the orbit of Mercury, quite possibly past the orbit of Venus, and by some calculations uncomfortably close to Earth's current orbit, though whether it actually engulfs the Earth or merely scorches it from very close range remains a genuinely open question among researchers, complicated by the fact that the Sun will also be losing mass during this phase, which would loosen its gravitational grip and allow the remaining planets to drift slightly outward, even as the Sun itself grows toward them. Eventually, in the contracting helium core at the heart of this swollen red giant, temperatures will climb high enough, somewhere in the neighborhood of 100 million degrees,
for helium itself to begin fusing into carbon and oxygen, a new nuclear furnace igniting within the old one. For a star of the Sun's particular mass, current models suggest this ignition happens suddenly, in an event called the helium flash, though the flash itself is thought to occur deep in the core, and would not be visible as any dramatic brightening from outside. After this, the Sun will settle briefly into a calmer phase of helium burning, smaller and hotter than it was as a red giant, though still much larger than it is now, before helium in the core also runs low, and the whole unstable sequence essentially repeats itself, swelling again into an even larger giant phase, shedding its outer layers in slow, gentle pulses. Those outer layers, drifting outward over thousands of years, will form a glowing shell of gas around the Sun's exposed core, a structure astronomers call a planetary nebula, a name that has nothing to do with planets, and everything to do with how these objects looked through the small telescopes of 18th century astronomers, appearing as soft, round, planet-like disks of light, rather than sharp points like ordinary stars. The nebula itself will glow for perhaps 10 or 20,000 years, illuminated by the intense ultraviolet light of the small, exposed core left behind, before fading and dispersing into the surrounding galaxy, its material eventually becoming part of some future cloud, perhaps even part of some future star. That exposed core is what will remain of the Sun in the end, a white dwarf, an object roughly the size of the Earth but containing something like half the Sun's current mass, packed so densely that a single teaspoon of its material would weigh, on Earth, something like several tons. It will have no fuel left to fuse, and it will simply cool, slowly, over an almost unimaginable span of time, radiating away its remaining heat like an ember, left in a dying fire, glowing faintly for billions of years, growing dimmer and dimmer, though never quite reaching a true absolute end within the current age of the universe. All of this, the swelling, the flashing, the shedding, the fading, lies so far ahead of us that it belongs to a different kind of time altogether, the geological, almost mythic time of stars, quite unlike the ordinary hours and years we measure our own lives by. Tonight, and for a very long stretch of nights to come, the Sun remains exactly what it has been for billions of years already, a steady, hydrogen-burning star, in the unremarkable comfort of its main sequence middle age, its core fusing quietly, its light beginning that long, slow climb outward, through the dense and shadowed region we are about to enter more closely, the radiative zone that wraps around the fusing heart like a thick and patient wall.
Let's come back, now, to the surface, one last time, and let the whole shape of the journey settle into place. Picture the Sun as you first pictured it in this telling, that shifting, seething skin of granulation, each cell of rising and falling gas about the size of a large country on Earth, each one lasting only some minutes before dissolving into the next. That surface was never still, and it was never going to be. It was the last visible sign of a churning that begins far below, in the convective zone, where gas too opaque to let light pass easily simply carries its heat, the way a pot of thick soup carries heat, in slow, turning currents of rising warmth and sinking cold. We traced that convection downward, layer by layer, until it met a strange, thin boundary called the tachocline, a transition zone only a few % of the Sun's radius in thickness, where the churning, differential rotation of the outer layers gives way to the almost rigid, unified rotation of the deeper interior. It is a quiet seam in the Sun's body, and it is also, many solar physicists suspect, though do not yet fully agree, the place where much of the Sun's magnetic field is generated and organized, the hidden engine room of a dynamo whose exact machinery remains one of the genuinely open questions in solar physics. Below that seam lies the radiative zone, that thick, patient wall of plasma we most recently entered, a region so dense and so opaque that light does not simply pass through it, but is endlessly absorbed and re-emitted, absorbed and re-emitted, in millions upon millions of tiny steps, a slow diffusion rather than a journey, the famous drunkard's walk of a photon that may take on the order of tens of thousands of years, by most careful estimates, to work its way from the edge of the fusing core to the base of the convective zone above it. And at the very center of it all, we found the core itself, a region only about a fifth of the sun's radius, yet holding nearly all of its mass in a space so dense and so hot, some 15 million degrees, that hydrogen nuclei are forced together against their mutual electric repulsion, fusing into helium through the proton-proton chain, releasing, step by careful step, the energy that becomes, eventually, everything we call sunlight. Threaded through every part of this journey were the neutrinos, those nearly weightless, nearly interactionless particles, born in the same fusion reactions as the light, but utterly unlike the light in how they travel. Where a photon might spend tens of thousands of years diffusing outward through the radiative zone alone, a neutrino simply leaves, passing through the entire body of the sun, through the convective zone, through the surface, out into space, and onward through the Earth itself, in a matter of seconds, barely touched by all that surrounding matter, because it interacts with almost nothing at all. For decades, the neutrinos we detected on Earth arrived in numbers lower than solar models predicted, a genuine and troubling discrepancy known as the solar-neutrino problem, one that stood unresolved for more than 30 years before careful underground experiments, built in old mines and beneath mountains to shield delicate detectors from cosmic interference, revealed that the missing neutrinos had not vanished at all, but had simply changed identity and flight, oscillating between different types on their way to us. It was a resolution that required rethinking not the sun, but the particles themselves, and it stands as one of the more elegant reminders in this whole story, that when observation and theory disagree, the fault is not always where you first suspect. And running underneath everything else we have discussed has been helioseismology, the quiet, patient science of listening to the sun's own trembling. The surface of the sun rings and pulses in millions of overlapping vibrational patterns, generated by the churning of the convective zone below, and by carefully measuring the tiny, rhythmic shifts in light these vibrations produce. Astronomers have been able to do something that once would have sounded almost like a magic trick: to infer the temperature, density, and rotation rate of layers, hundreds of thousands of kilometers beneath the visible surface, without ever touching them, without ever seeing them directly. It is worth pausing on how strange, and how quietly remarkable this is. No probe has ever been sent into the sun's interior, nor ever could be. Everything we know of that hidden architecture, the depth of the convective zone, the sharpness of the tachocline, the rotation of the core, has been reconstructed indirectly, through starlight, through neutrinos, through the careful mathematics of vibration, gathered patiently across generations of astronomers, who each added one more piece to a picture none of them could see whole in their own lifetime. It is worth being honest, too, about what remains unsettled in that picture: the precise workings of the solar dynamo, the mechanism that builds and periodically reverses the sun's magnetic field on its roughly 11-year cycle, are still actively debated, with different models placing different emphasis on the tachocline, on near-surface flows, and on the deep interior, without full agreement yet on which processes matter most. The opacity of the solar plasma, how strongly it absorbs and scatters the radiation trying to pass through it at each depth,
has been a persistently difficult quantity to calculate precisely, and small revisions to opacity estimates over the years have sent ripples through solar models, at times even briefly disturbing the hard-won agreement between theory and helioseismic observation. And the rotation of the deep core itself, whether it spins at the same steady rate as the radiative zone around it, or slightly faster, or slightly slower, remains an area where different studies have reached different conclusions, the signal at those depths being faint and difficult to disentangle from noise. None of this uncertainty undermines the broad picture we have built across this long night together. It simply means that picture still has soft edges, places where careful people are still working, still measuring, still arguing productively over data that arrives in whispers rather than shouts. What is certain, what generations of that patient measurement have firmly established, is the outline of the journey itself. Deep in the core, hydrogen becomes helium, and in that transformation, mass becomes energy, in the precise and now well-tested relationship Einstein once described. That energy begins as high-frequency gamma radiation, ferociously energetic and utterly unlike the gentle light that later reaches your skin. It spends its long apprenticeship in the radiative zone, softening and reddening with each absorption and re-emission, losing energy at every step even as it grows more patient, until it reaches the convective zone, and is finally swept upward not by diffusion, but by the physical motion of rising gas, carried the rest of the way to the surface in a comparatively swift, final ascent. It leaves that seething, granulated surface as visible light, ordinary sunlight, the kind that has already been walking and drifting and rising through the sun's body for tens of thousands of years, before it ever escapes into the dark. And then, at last, comes the shortest and simplest leg of the entire journey. Once that light leaves the surface, it crosses the 93 million miles of largely empty space between the sun and the earth in a little over 8 minutes, at the ordinary, unchanging speed of light. No diffusion now, no absorption, nothing left to slow it. 8 minutes is nothing at all, set against the tens of thousands of years that came before it. A final, brief, uninterrupted sprint, after an almost unimaginably long and patient climb. It is a strange thing to hold in your mind as you lie here in the dark, that the warmth you might remember from this afternoon, or the last bit of daylight fading from a window somewhere in the world tonight, began its existence as a fusion reaction some tens of thousands of years ago, in a place no human eye will ever see directly, and only in its final moments did it move quickly at all. The sun, in its own unhurried way, has been doing this every day, every hour, every second, for about 4.5 billion years, and by every careful measurement we have, it will keep doing so for billions more, its core steadily converting hydrogen to helium, its radiative zone patiently passing that energy outward, its convective zone stirring and folding, its surface flickering with granules that live and die in minutes, all of it settled into the long, steady rhythm of an ordinary star in the middle of its life. Whatever remains uncertain about the fine details of its dynamo, its opacity, its innermost rotation, the great outline of the journey, from core to surface to your window, is no longer a matter of guesswork, but of decades of careful, indirect, hard-won listening. Rest well.